We're moving on to a new topic now. The topic's going to be sets and basic operations on sets. What is a set? A set is an unordered collection of objects. So, for example, we could let the set V be A, E, I, O, and U. This is the set of vowels in the English alphabet. We use these curly braces to denote the beginning and the end of a set. We could define another set, O, to be 1, 3, 5, 7, 9. And this would be all odd numbers less than 10. We could also, and we've seen before, the natural numbers. This is 1, 2, 3, 4, and so on. I use these little dots here to denote that this list goes on and on. Another way of writing sets is to use something called set builder notation. So for example, we could write O as the set of all x such that, that's how this vertical line is read. It's read as such that. So it's the set of all x such that x is odd and x is less than 10. That's an alternative way to denote the set O. How about the rationals? We've seen those before. These are the set of all x such that x is equal to p divided by q, where p and q are integers. You may be familiar with these other sets, so we have closed intervals. We'd write the closed interval AB. This is the set of all x in the real numbers such that x is greater than or equal to A and less than or equal to B. And we have the open interval AB. This is the set of all x in the reals such that A is less than x is less than B. Now remember, sets are unordered collections of objects. So the set 1, 3, 5, 7, 9 is equal to the set 9, 7, 3, 1, 5. It doesn't matter in which order elements are listed in a set. And two sets are equal if they contain the same elements. There's also something called the empty set. This is a set that has 0 elements in it, and it's written as either this, open curly, close curly, or sometimes it's written using this 0 with a line through it notation. So some more notation. How would you write that an element is a member of a particular set? Say we wanted to say that, say we have the set O, 1, 3, 5, 7, 9. We can write that 1 is an element of this set by saying 1 and then this symbol O. So 1 is an element of O because we see here that 1 is sitting inside the set. 2/3 is an element of the rational numbers. We've also seen in class that the square root of 2 is not an element of the rational numbers. So this symbol, this kind of looks like a little e, is you would say this 1 belongs to O, root 2 does not belong to Q, or you can just say 1 is in O, root 2 is not in Q. Now let's say we have two sets. Let's say we define O prime to be 1, 3, 7, and we want to indicate that every element of O prime is contained in O. We write it this way. We say O prime is a subset of O. More generally, we write that A is a subset of B if for every x, x in A implies x is in B. So A is a subset of B if and only if every element of A is also an element of B. Two special facts to notice here are that for any set A, the empty set is a subset of A, and also for any set A, the set itself is a subset of A. This is because any element in A is also an element of A. So the empty set is a subset of A, and A is a subset of A. And we could draw a picture. These are often called Venn diagrams. So for example, so this rectangle usually denotes some giant universe of objects. So for example, this rectangle might correspond to all rational numbers. And then we could have a set, a subset B of rational numbers. Maybe this is all even rational numbers. And then we might have A here. So you have drawn A to be a subset of B. So, maybe B is the set of all x such that x is in the rationals and x is even. And maybe A is the set of all x such that x is in the rationals and x is a multiple of 4. So B here is going to be this larger circle. It is a subset of the rationals. And A is a subset of B because if you're a multiple of 4, then you're also even. So just two more definitions that I'd like to make about sets. One is, so if A is a set, then the power set of A is the set of all subsets of A. So for example, if A is the set 1, 2, then the power set of A, it's usually written with this script P, is going to be the set of all subsets. So this would be first the empty set, then the singleton 1, then the singleton 2. A singleton is a set with one element in it. Then the set itself, because we said that A is always a subset of A. Okay, so here are all 4 subsets of A. This is the empty set, which is a subset of any set, as we said earlier. This is A itself. We said that, A is always a subset of itself. And then here's a set with just 1 in it, but that's a subset of A because, 1 is in A, and 2 is a subset of A too. Okay, we could also do 1, 2, 3. This is going to have the power set of B is going to have 8 elements. The empty set, 1, 2, 3, 1, 2, 2, 3, 1, 3, and then 1, 2, 3. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set of B. And finally, let me define the Cartesian product of two sets. So if A and B are sets, then we say that A cross B, this is called the Cartesian product, is the set of tuples. So it makes tuples out of these two sets, A and B. So it's a set of all tuples a, little b, such that A is in A and B is in B. So for example, if A is the set 1, 2, and B is the set 3, 4, then A cross B is going to be, well, 1, 3, 1, 4, 2, 3, and 2, 4. Okay, so it's going to have 4 tuples. So, you take one element in A and you add on every element of B here. So we have 1, 3, 1, 4, and then we have 2, so we have 2, 3, 2, 4. So if A has m elements, and if A has m elements, we write that the size of A equals m, and B has n elements, we write the size of B is n, then the size of A cross B is also equal m times n. As you can see, the sizes will multiply when you take the Cartesian product of two sets. Now, oftentimes, instead of saying the word size, we'll use the word cardinality. But when you see the word cardinality, you should think this is roughly equal to the word size. And if you're looking at the cardinality of an infinite set, like the natural numbers, for right now, we'll just write that using the infinity symbol. And the cardinality of a finite set is just the number of elements in that set. So the cardinality of A here would be m because A has m elements. The cardinality of B is n because B has n elements. The cardinality of A cross B is m times n. And the cardinality of an infinite set, the natural numbers, is infinity. Oh, one last brief note. The set A cross B does not equal the set B cross A, because the set B cross A is going to be, well, first we do 3 elements of B and then elements of A. So 3, 1, 3, 2, and then 4, 1, 4, 2. So notice that A cross B had elements of A first, B cross A has elements of B first, and these are, as you can see, these are different sets. We have 3, 1 in this set, B cross A, but you don't see 3, 1 anywhere. Here you see 1, 3.